And it turns out that A has 31,031 chances out of 46,656, or 0.6651 chance of winning. And B has this, which is 0.6187. A wins. Right? So is Pepys satisfied with this? Pepys writes back and he says, why? Right? I cannot bear the thought of being made master of a jewel I know not how to wear. Right? So he's willing to swallow his pride to search for really solid understanding. Now compare this with a comment we got at the end of semester evaluation in January a year ago. Okay? I never went to his office hours for help because I felt like he would make me feel stupid because he's superior to me in chemistry. I hope I'm superior to you in chemistry. I'm not superior as a person, but I hope I'm superior in chemistry. You're paying me the big bucks, right? Because of that. So swallow your pride and ask someone for help. Okay? Follow Pepys. So read Pepys and Newton and get together to do problems for Monday. And contribute to the wiki when you're asked to do so. So here are problems. For Friday, the problems are optional but very helpful. One is find out which two class members have the rooms nearest you so that you can maybe use them as study partners. You don't have to use them, use anybody, but use someone. Don't try to go it alone. 2, what are the 3 most common items of advice from course veterans? So if you click there or go to the web page, you can get anonymous advice, right? I was careful to make it sure it's anonymous. So you can get much of it is contradictory. So your job is to look through it and try to get some idea of what they're telling you that's worth knowing. For Monday, there are problems from that web page, Pepys and Newton. And let me tell you that you better get together with other people to do it because there's a lot of stuff there. So get together in a group, parcel out who works on what, discuss what went on, and so on. And then for a week from Friday, there's stuff about drawing Lewis structures from another web page about functional groups. So we'll get to that later. I just want you to know what's coming up. Incidentally, this thing about the problem set that has to do with the mathematics that Newton and Pepys were working on there has to do with isotope ratios. You know, chlorine has a funny atomic weight. Why? What is the atomic weight? Does anybody know? 35 and a half. Why a half? Most of the elements are pretty near integers. It's because it's a mixture of isotopes, right? It's a quarter of one isotope and 3/4 of the other, and the average is 35 and a half. It's 35 and 37. Okay? But in fact, it depends on where you get chlorine from, what the ratio is. There's 35 and a half, right, for a standard atomic weight. But it ranges quite a bit depending on where you get it. So by measuring these ratios, which is a lot like these odds in the betting, you can tell where things came from. You can tell where hydrocarbons came from sometimes that way. And those are the problems that you have to deal with. So it's not really very, very relevant to the course as a whole, but it's relevant to the Pepys and Newton thing, and it's a fun problem. So that's what you got to do for Monday. Okay, and here are the assignments. I emailed all these people. I hope you're here, and that you picked up on what we talked about today so that you can improve the wikis from last year. Last year, people developed their wikis from scratch. This time, so it's a very valuable thing to do. So I was torn this year as to whether to have you do them from scratch or whether to modify last year. I figured modifying last year is better because then you have something to read earlier on for those who are not working on developing it. So anyhow, but the hope is, so if you modify it, it has to be some significant, not put a comma in or something like that, but add something useful to understanding. If you do it within 36 hours, you get 2 points, and if what you do is really good, you get 3 points. Okay? So you go to that page and you click on those things, and then you can read, or you can either modify them or read it. It's a wiki. Now we come to the question that we'll address more. We have another 5 minutes here. the question we're really dealing with now, having seen how to work in Chem 125, is, are there atoms and molecules? How do you know? Right? And what force holds them together? Because if we knew that they're real, and we knew what force held them together, then in principle we might be able to calculate everything. Right? So it would all be theory. So is it springs that hold atoms together? So Robert Boyle, notice he's right at that time, 1627 to 1691, and he's the oldest person that's on the honor roll outside the building here. He's over that way. So Robert Boyle wrote this first important book in chemistry, New Experiments Physico-Mechanical, touching the spring of air, right? So you know Boyle's law, right? How pressure and volume change. That air in a piston acts like a spring. And so PV is a constant. That's Boyle's law. So he developed this science on the basis of a new instrument, the pneumatical engine, which was built by Robert Hooke, the guy we quoted. And there's a picture of the air pump here with that crank on it and so on to pump things in or out of that bulb. Now, a couple of years later, Hooke wrote this book, Lectures de Potentia Restitutiva, or of Spring, explaining the power of springing bodies. And this is the beginning of that book. The theory of springs, though attempted by diverse eminent mathematicians of this age, has hitherto not been published by any. It is now about 18 years since I first found it out, but designing to apply it to some particular use, I omitted the publishing thereof. So he kept it secret so no one would steal the idea. What did he hope to do with a spring? A really important technology that he could do with a spring. It was a coiled spring that he invented. A new kind of clock, right? One that could work better for navigation. And it was his spring that actually allowed Harrison, 100 years later, to win the contest about making an accurate clock. Some of you must know that story. So anyhow, he had been hiding this so it wouldn't be stolen. In fact, it was stolen by Huygens. So about 3 years since, His Majesty was pleased to see the experiment that made out this theory tried at Whitehall, and also my spring watch. About 2 years since, I printed the theory in an anagram at the end of my book on the description of helioscopes, viz. This. So this is what he published at the end of this book on helioscopes. And that is an anagram of how springs work, right? So that later he could prove that he knew it, if needs be, but no one could steal it in the meantime. Right? And if you unscramble it, it's ut tensio sic vis. That is, the power of any spring is in the same proportion with the tension thereof. That is, if one power stretch or bend it one space, two will stress it two, three will bend it three, and so forward. So here's his figure that shows that. That's Hooke's law, the force law. The force is proportional to the distortion, right? So here's his figure, and he's got plots of it here. Ut tensio, as the extension, sic vis, so the force, so it's linear, right? The force is how much you stretch it. And he has lots of different kinds of springs that do that. Here's this clock kind of spring, a coil spring, just stretching a wire. So the force is proportional to the extension. Or another way of saying it is the potential energy is proportional to the square of the extension. So it's a parabola. So that's Hooke's law, right? And that's where we'll take up next time.